there's 18 people on that list, so we're going to get right into it. Right, watch for announcements for a spring full conference. Before we get into our fun physics day, Jeremy, do you want to make an announcement?
Many of you know Amber Stuver, who has served as our section rep for about the last 5 years or so. Unfortunately, she passed away about a week and a half ago of natural causes, but it was sudden, it was unexpected. So all of us at Villanova are still in shock over this. She had revolutionized a number of our courses, including the freshman sequence for life sciences majors, bringing in some real new pedagogical techniques. Had also completely revamped our computational physics sequence. Done a lot of service for SEPS as well. You remember she's, I think, given a couple of talks on LIGO and gravitational waves, which she was happy to explain to anyone who would listen, and if you were smart, you did listen. Usually said she was one of the few people that the high up heads allowed to talk to the regular people. So her loss is a great loss for the physics community in this area and nationwide, in fact. She'd served on a number of committees for the National AAPT, the APS, and the AAS. I think, though, she'd be happy to see us here sharing some physics ideas and sharing our love for physics teaching. So I think we should go ahead and have a great conference and remember Amber. Thank you.
As I'm sure your students point out to you every year, why isn't there a unit for momentum? So I am trying to get physics teachers to make the unit for momentum. It's the Noether, in honor of Emmy Noether, whose theorem predicts conservation of momentum, among other conservation laws, and also because of all the units in the SI system, there are 0 named for women. So it's about time to change that as well. So just start using it. I actually got a letter published in the AJP recommending that we do this. This is a revolution that starts from the grassroots. Once we're all doing it, the BIPM in Paris will have to listen to us.
And what's the symbol?
What?
What's the symbol?
It's NR.
NR.
Right? First letter, last letter. Capital N, small r. Noether.
So,
are we about to be?
no, you were about to be. Notice, I've had this for many years. I was in the basement yesterday. Very good balance. Moves. It's called Crawling Baby. You can't get it anymore as far as I know. The sort of interesting thing, this was my first, I've had a couple Crawling Babies, is that this one doesn't seem to stand up very well. Whereas this one, even, now you're doing it, does stand up pretty well. Any idea why?
Batteries. One has batteries.
And not just batteries, but
The female baby is a lower center of mass.
which is the female baby? They. They're theys.
So this is a new test for sex.
Wait 6 months and the other one will be.
But where are the batteries?
In the butt.
In the butt, yeah.
right.
The batteries are in the butt here, so that even though she has a lot of stuff forward, center of mass still ends up being above the feet. The batteries are not in anymore. You can get her to balance. This, you can tell, is a somewhat meaner version of the Crawling Baby. But main thing I wanted to show is this. I have it just wrapped up. You can see behind me a site. I brought this up before. It's called Grand Illusions. I don't know if anybody's ever seen or heard of it. It's a magic, but it's really, even when you see a listing of things that they have up here, it's got lots of very interesting, not too expensive things. For example, I don't know, a year or so ago, I think I brought a tensegrity device, which is a little table that has some support very interestingly, and a ton of different optical illusions that are available. Some you sort of have to see, and for some of them they have little video shorts. They have
British site, the CBA.
yes, it's a British site. They do ship, and it's not really that terribly expensive. Now, some of the things they have here are. The moire cards, can you tell from where you are what that is? Huh? Girl of the Pearl Earring. It's one of the few that, when you look at it closely, all it is are just colored blocks. Some of them have highly detailed little drawings, so that they're so small that you could almost put anything in their place. These, they're just colored blocks, and yet from a distance, it gives you the impression that this is, I think, 4 or 5 postcards. You get different works of art. There's some scopes here, an upside down scope, reversing goggles, and then this is a fairly good one, the hollow face illusion. A lot of these I have. And then you can see on the right a Hyperscope kit, which is for £20, but it includes the VAT. And the one I have, the Hyperscope Pro kit, which was a little bit more, but I had the earlier one, and it was a little smaller, and this time I decided to spend a little more and get this version. I don't know, has anybody ever seen a Hyperscope? You're not going to be able to see. Well, here, if I stand here, can you see where my eyes appear to be? They're not here. They're about there, about there. They're spread apart further, and well, what that does. It's a pity optics isn't taught as much anymore. It's even just geometric, but it is still taught some places I get here. But when you look at things, especially along the line of sight this way, if you're looking at just some point in space, here's an eye, and here's an eye, and to get a sense of depth, you look from one eye in one direction and the other eye's in a slightly different direction, and you get, especially against the background, you get a jump of position against background. That's parallax. Excuse me. But if your eyes were further apart, which is kind of physically hard to do, then I'll just draw it behind here. If your eyes were like this and this, you get a much bigger, excuse my light not traveling in a straight line, but you get a much bigger shift, a parallactic shift, when viewing something. And that's what all this does. It just has two sets of mirrors on one side, 2 sets of mirrors on the other side, and basically it takes the light, goes here's one, and goes to one eye, but it's as though your eye is seen from this position, and likewise the other side would have the other eye going to this particular mirror. And so what it's doing is giving you eyes that are spread out further. It's cool. Now, some people, my wife, don't see the effect as well as other people. I don't know why necessarily, but and what I'll do, I'll pass this around, and the only thing I ask is that you don't put your hands on the mirrors that are here. Other than that, just take a look. Depth, again, along this line is what's really noticeably different. Basically, if you take an arm, the arm will have different points along it, which will seem to be noticeably separated spatially from one another. The net effect, it makes your arm appear somewhat longer, or you say there's something different about this, but it's along that line. Also, if you have two things that are spatially near one another, maybe one's a little bit further back, when you look at this, you see that as a noticeable difference. Like, oh, there is depth between the two things that you wouldn't normally be able to see because it's more sensitive to this parallaxic shift between objects at different distances. So, yeah, I don't know. I wouldn't suggest driving. The mirrors, what's the sign say on the right side? Yeah, this one is just, you're screwed if you drive with this because everything is a bit different. And start there. And that's it.
I'm Geoff Wetherhold. I taught at Parkland High School in Allentown for 35 years. I retired in 2020. In spring, I was hired by Muhlenberg College to teach an evening course, and then they kept me on, so I've been there since 2020. And I teach one of my favorite courses, Physics for Life, at Muhlenberg. So it's basically we use conceptual physics by Paul Hewitt, and it's for non-science majors. And that was always my favorite course to teach at the high school, but it was always a dumping ground, unfortunately. So you had kids in there that I didn't blame them. They really didn't want to be there. You know, they wanted to do other things. But so now, you know, you have students who really want to get a good grade and do well. So anyway, but this video is kind of cool that I made. So let's see if we can figure out what's going on. I call it the mystery video. I'll show it again. So there's no hill, there's no strings attached, no magnets, no smoke and mirrors. Okay, no photography trick or anything like that. What do you think's going on there?
My first question is, did you record this accidentally or did you set it up?
No, I set it up.
Okay.
Yeah.
I've recorded things that I can't explain it.
Well, this still confuses me sometimes when I watch it. Like back there, I was like, okay, now what's going on? You know, before I. So you know, since that cup is accelerating, there must be a force acting on it. To which way? There must, from Newton's second law, right? There has to be a force acting to the right. So the question is, what's providing that force?
I think it's on a board which is tilted.
No, it's not tilted.
Oh.
Yeah, it's not on the hill. It's level, just like this. So.
Well, it's coming to a stop.
Oops. So this is what you see. So to make a long story short, I mounted the camera on the board, okay, and then I accelerated the board that way. Okay, so the cup wants to stay at rest, but there's friction, which takes it that way, relative to this. So it's like mind-boggling. Yeah, I guess I might try. Let me see without breaking the cup, which I probably will.
You want somebody to help catch it?
Yeah. Let's just give it a shot here. So I go. Nope, it's the other way. See what I mean?
Wow.
Yeah. Right. So I should be going. I'm totally confused. You get it, right?
That was the video perfectly.
Okay. All right. The other thing I want to show you, just little things I really liked over the years, but I probably saw this at a physics demonstration show a long time ago, but I took these lights and put blue tape on it, put this one at the center of gravity, and this at some other odd place. And it's really nice in a darkened room. When you throw this, right, you see this follow a nice smooth parabolic path, and then this one a crazy path. So you don't have to like film it with a video camera or anything. Kids can actually see that. So that works really nice. Sure. Someone want to catch it? Anyone good at catching? Okay. So I need someone over there to catch it.
I'll do it.
Okay. That's all right if you don't. It's. And then back.
Which way? So this way or this way?
It doesn't matter, yeah.
Yeah, there's a parabola.
All right, another thing that's really cool is a simple Doppler beat demonstration. I don't know if any of you ever tried this. You just strike the tuning fork and you walk toward a wall, and the students hear a beat frequency. It's that simple. All right.
If you say so.
Well, you guys should be able to hear it. It's funny, when I first started doing this, I was run. And I forgot that that's not it would be. I thought if I should run fast, I could do that. It's actually going to go slow. So I was doing that for like 20 years. And then I finally figured out, well, maybe if I just do that. And then, another one that I have done is really cool. If you want to measure, like if you have an apparatus which we all do probably. I don't do this with the physics for life, by the way. These are mostly, well, except for like the Einstein thing I do, but I don't do internal force with physics for life. So this is from the old high school when I did AP courses. So so if you have two parts butted up against each other, and this is on an incline, and you want to know what the force is between the cards. Right, between the cards. Right, so what I did is I rigged this up with a force sensor, 2 pencils I stole and broke in half, and then what you do is it butts up against it, and then you tie. I put a wooden dowel here and put a little cut in the wooden dowel, and then you put the string. If you have a string, you just put it here, and then it runs over the pulley. So this card is pulled along, right, and then the force sensor measures the internal force between the two cards. It works really well. It's such a simple design. You get it?
Yeah.
What do the principals do?
Oh, they just hold this in place.
You don't want that to slide.
Yeah, you don't want this slide. All right, and then I think a while ago, I wasn't able to come to a demonstration, and I think you did for me, Bob. Was it you with this? Right, remember that?
I remember.
So this is kind of cool. I do this a lot with Crucible. I wasn't able to come to demonstrate it, and I think I told Bob just do it or something to show. All right, so what you can do is just do finger measurements. All right, I can't do it. I wish I had that third arm yet. Right? If you measure, do you think with a finger measurement you can do that?
Sure.
You know what I mean by finger? Just kind of like that. Like this.
Like
Yeah, yeah. And then keep the angle.
Okay.
And slide it up. No, you have to keep the angle.
Oh,
And
sorry.
slide it up to meet this top. Nope, keep the angle.
Head to toe, head to toe.
Parallel.
Parallel?
Yeah.
Like this?
For head to toe.
Yeah, just go all the way up to the top. Here, why don't you hold it?
Okay.
Because I know I'm not explaining it, just turn around. And again, this is a repeat, so angle this a little bit, make it more.
Like this?
Yeah, that's good. So if you do this, you go up to there. Okay, now just support it by one. Okay, now bring it up so that it meets, and you can see it's right.
Wow.
So the other thing you can do with these is center of mass. Right, so figure out where the center of mass is, which is about right there. Okay, and then if you drop them at the same time, they fall together. So it's kind of like that slinky drop, but it's a little, but the kids can actually figure it out. You know, with the slinky, it's a pretty complicated math that's involved to figure out the center of mass of a stretched slinky. Right? You've got to use calculus probably to do that, I would think. But if you do this, right? I think that's it.
So I retired in 2011 from high school teaching at Westtown, and then I worked at a couple other places. And I was able to keep some of the stuff. But as I was closer and closer to moving into a retirement village, I realized I had to get rid of everything, so I still have some stuff to give away. I had a very nice demo on capacitors. Something I just love is AM radio operator water capacitors, how do they work, blah, blah, blah. And I thought, oh, it's September, nobody cares about capacitors, and maybe you don't even teach that anymore. So I thought, well, what's everyone doing in the fall? What's everyone doing? Probably motion. So what can you do with a ball and a motion detector, which I didn't bother to bring? What can you teach with these things? So my slideshow is what I have done or had done really a couple decades ago, but I thought it might be a refresher. All right, so what can you do? One of the things you can do is, and I don't start with this, is just show what motion detectors can display. The last couple of years I was teaching ninth graders, and they're just learning about graphs. So if something's moving at a constant speed, so we did something like this, just roll a ball down across a level table and have a motion sensor here and what kind of graph results. And that was nothing exotic, right? So a position time graph was, well,
Drone velocity?
yeah, the back one. So something was, no, not that one. We want to go back. Oh yeah, that's it. Yeah, so it wasn't moving, right? But it wasn't on the sensor. It was a little bit off the sensor because you can't get too close. And then there the ball's rolling on a tape. You know, that's nothing very exotic there. So what else can you do besides constant motion? Yeah, it's nice to start with constant speed, constant velocity. Next. So what about if something's gaining speed, changing speed, then what do? Well, I used to roll a ball down a ramp. That was easy to do. So if you roll a ball down a ramp, you can get things. But here the velocity is negative, and here it's positive. So how did I do that? So just tilt the ramp up and have the motion sensor. As the ball rolls up the ramp, the ball rolls back down the ramp. So here's a velocity is changing, but the rate of change is constant. The slope's constant. How come? Well, because in this case it's on a constant angle ramp. So that was pretty easy to show, or I'd have the kids do that. I didn't show it. Next slide. So what if you look at a position time graph of same thing? The ball rolls, I used a can, they get better echoes. Can rolls up a ramp, stops for a moment. Can rolls back down. So here's a nice, and especially ninth graders, they're not used to seeing curves. They're barely learning about slopes and lines. So all this is like, whoa, what was that? So that was kind of interesting. But after they did that, I said, well, could you make a prediction based on that? What would a speed time graph, a velocity time graph look like? And I'm, what? That was pretty good extrapolation. Some of the kids saw it right away because they saw the slope was the speed. So of course this starts out, it's not moving. all right, position is constant. Then the slope's pretty steep, gradually, but up here the slope is 0, and then it's coming back the other way. So that was kind of a leap mathematically, especially for 9th grade. For juniors and seniors, that was no big deal. Excellent. So what would the velocity time graph look like for that previous slide? And I'd often have them do something with a motion sensor and try to make a prediction. What would happen if you move the motion sensor to a different part of the ramp, or whatever you do. And these were the earlier vernier motion sensors, and they were pinging at about 20 times per second, 20%. So here's the velocity graph of that. It's not moving, then suddenly something's happening here. I pushed it or something. And then that was kind of interesting that the velocity was a line and negative slope. So why did the velocity do that? A lot of this would be an interesting discussion. Let the lab tables fight amongst themselves. What's the meaning here? But the can was rolling in one direction. It stopped for a moment, right? Then it rolled back down. And that's pretty clear data. I didn't bother to fit a curve to this. Next slide.
Wait, Barry.
Yeah.
I don't see that. Where did the velocity stop?
Here the velocity is 0. Here it's a +1, -1. So right there, the velocity is 0.
Oh, that's got it. Okay, thanks. I was looking.
That was a good question. I'm assuming a lot. Next slide. So what about the acceleration of the can? Well, this is where the 9th graders would just what is acceleration? They often would think of it as velocity over time, not change in velocity over time. That happens to everybody. So what would be the acceleration? Let's go back a second. What would be the acceleration when when the can is not moving? That's here. The velocity is 0. Everyone sees the can goes up, rolls up, stops. At the moment it stops, what's the acceleration? And I'd say 99% of all my class, especially in 9th grade, would say 0. It's not moving. That's a interesting idea because they have in mind acceleration is just velocity over time. Velocity is 0. So I'd say, throw a ball up in the air for a moment. What's the acceleration when the ball is at the peak? And they all say 0. I said, I don't want to stay there for the next century. Right. So acceleration is how the velocity is going to change. So every day for the next week, when the kids would come in, I'd say, so accelerations, and they'd all say, change in velocity over time. So it was worth it just for that. Next slide. So how about a falling object? So just, that's why I brought the ball in. So just a motion like this. The sensor was up here on a ring stand, and I didn't use this. I'd actually use like a medicine ball or something. So they see the velocity is going up, but at a pretty steady rate. The rate of the velocity gain is pretty steady, which implies the acceleration is. Next slide. I asked the kids to think about this, and I rarely even see this in the basic text. And I asked Paul Hewitt about this. He said he didn't want to get into this. So what if you plot velocity versus not time, because everyone sees that's linear, velocity against the distance it's falling. And yet what the 9th graders is called sideways problem. How come? So that was an interesting thing that I had never thought about. And like Paul Hewitt didn't want to mess with the mathematics of plotting anything against time. So this is the one where this was the most fun. What about a bouncing ball? I gotta watch it. So predict the motion of a bouncing ball. Let's say 3 bounces, and we'd bounce against the floor. And I used to really blow up hard like volleyball, so they really had a nice bounce, and they were big enough to get a good echo. So here's one. This was like from 2008 or something. I don't know. I just went through old slides. So here the ball's not moving because someone's holding it. Then you drop it. So as you drop it, it's moving away from the motion sensor. So it's positive distance. Somewhere up here, it hit the floor. And that was about 2 meters. So, the typical ceiling height. And then here's the ball. So what's the ball doing here? It's coming back up towards the motion sensor. Where is it right here? It stops. So this is the bounce, or the first bounce. Here's the second bounce, the third bounce. So that was surprising to them, that first they're curves, and they kind of mimic, but they don't exactly duplicate, because with each bounce it loses, some energy, but we're going to talk about that. Next slide.
Floor elastic, what's that about?
Yeah, well, when it hits the floor, that's 2 slides ahead, of course, Bruce. So we're going to look at what happens right there. Remember, the motion sensor's up here looking down. So when the ball hits the floor, it's at the greatest distance from the motion sensor. So that's it, hitting the floor. Or somewhere around there.
Elastic.
Oh, I don't know.
Sampling.
All right, so what's the shape of each curve? Well, I wouldn't do that with 9th graders, but it's kind of interesting. Like, well, they have similar arcs. Is that, what's going on? Next slide. So they're all quadratics. They're all parabolas. Why? And if you do a curve fit, this gets a little exciting with the Vernier stuff. If you do a curve fit, the A term here, ax squared plus bx plus c, the A term 4, the A term 4.9, 4.7. The A terms are all about 4 to 5. How come? And you can get interesting things about what's the derivation of the 1/2 AT squared. So the A is 1/2 G. Kind of interesting. Next slide. This is the one that usually confuse them. So if you look at the velocity of the bouncing balls, first, it's not moving. Yeah, it's a big deal. Here it's moving, but remember, it's falling, so it's moving away from the motion sensor, so the Vernier software calls that positive. So the velocity is increasing positive until it hits the floor. And then what's the velocity? It's a negative number. How come negative? Because now the ball's coming closer to the motion sensor. Negative, 0, positive. So if you fit lines to these, you find the slope is pretty much the same. And the slope's the acceleration. It's about 9.5 or so. Now, coming to Bruce's. What about the acceleration of the bounce? It's not free fall, right? It's touching the floor. So that's an interesting one, and the data here just shows roughly that a bounce takes about 2 dots. That's about 2/20, 1/10 of a second. So the interaction with the floor is very rapid. But the acceleration during that moment is negative 68, negative 55, negative 58, so that's about a 5-6 G acceleration. What's the direction of the acceleration? What's the acceleration during free fall? That also is kind of interesting in the sense of acceleration can have a plus or a minus direction. What else can you do with a ball? So this is going to be real fast. What about other laws you want to teach? Like, how about if we get to energy and we look at the potential energy of a ball relative to something like table or the floor? And as you let it go, look at the kinetic energy and look at the potential energy and plot that versus time. So the potential energy, the ball's up here, it's not moving. It falls, so it loses potential energy. So in terms of the software, MGH, I didn't care about M, I didn't care about G, I was just plotting H. Then the rest is all kind of fake. So here's the height, or the PE, bounce, bounce, bounce. And of course it's losing potential energy after each bounce. Look at the kinetic energy, 0, it's gaining because it's falling, hits the floor. So you notice that both are kind of, going up, going down. What if you add the potential and the kinetic? You get, before the bounce, right here, conservation of energy. So that's about 15 joules worth. I forget the mass of the ball. The second bounce, it's constant, but it's only 11 joules. The third bounce, 7.5. So that's kind of interesting that if you look at the sum of the KE and PE, and it's just using a $100 motion sensor on a ball, you get some interesting results about conservation of energy. I don't want to just ask the kids to finish. So it's losing energy, and they can see that here, it hits the floor, it hits the floor. Does it lose the same percentage energy with each bounce? That was kind of an extra credit thing to think about. There are a lot of other things you can do with a ball and a motion sensor, but that's all I wanted to bring all the time in the show. That's it.
Hi there. My name is Christopher Brown. I am an assistant teaching professor at Villanova. Been there for about 6 years, and I was lucky enough to go to Temple's CAT conference this past January, and the theme of the conference was generative AI. which I think has kind of been on at least your students' minds, if not on our minds as well. The homework apocalypse is here. It's a whole thing. So I came back with some really great ideas, mainly based on a presentation by K. DeVoe and C. Eager. The QR code on the back of the visual aid goes straight to their presentation, which I think is a little bit more detailed than mine and better cited. This isn't really as much of a demo as some of the other ones, but Jeremy said it was going to be okay, so if it's not okay, blame Jeremy. So if you wanted to follow along, you can do so here. But I'm talking about renewable assignments today. And the whole idea here is just kind of disarming the AI dependence. And to do so, some of the ways that I'm trying to do that is to prioritize human interaction, personal experience, so process-based learning especially. I mean, that's something that we do a lot in labs, but also bring it into our lectures as well. And then a little bit harder to do in some of the physics classes is local knowledge and community building, but it's still applicable here. So some of the things I'm at least considering are assigning current topics. What kind of recent posts on phys.org is accessible to students that they can kind of start talking about in the class. Multimedia creations, allowing them to kind of make something, an artifact, if you will. Engaging with primary experience, primary sources, and then also reflection and conducting peer review is also another way to really have that experience-driven education. So what does renewable mean? So we've kind of said, okay, trying to get away from AI, why renewable? It's the idea of a renewable assignment is that it's made by students. It has value in and of itself beyond just the supporting the student creators' learning. And then it's also publicly available, distributable, and open licensed. So you can reuse it, revise it, and it's now part of kind of this learning community rather than just kind of locked down for your students' own use. Wiley and Hilton kind of had a really nice chart on this, talking about disposable assignments, really just for the sake of learning for the student, which is great, but authentic assignments kind of go beyond that and has value in and of itself. And then constructionist and renewable really start to bring in that artifact is made public and it's also openly licensed. So, why renewable assignments? Really it goes back to open educational practices. This idea that we're trying to have an equitable learning environment, and also something where students are shaping the knowledge that they're kind of being a part of as well. The 5 R's is kind of, they talked about in the presentation. I'm modeling this off of our redistribute, retain, reuse, revise, and remix. Those aren't necessarily needed to be in that order. Kind of the beauty of the 5 R's is that you can kind of go in any which way. I kind of structured them in a circle, but any of these, you could start with reusing something and then remixing it, redistributing, revising, retaining, which I think is kind of cool. So the main point I'm trying to get at here is that renewable assignments are focusing on process-based learning by definition. They require context, which is something that generative AI kind of is, well, not as much struggling with, but it's still something that it doesn't have. It does not have the same context that your students have going into an assignment. So really focusing on that context, I think has helped me try and change some of my assignments up. So let's talk about some, thank you, slide, for reminding me. Before we talk about, some examples, it might be worth asking if this assignment is easily done by generative AI, is it worth doing? And a lot of times the answer is yes. A lot of times the answer is yes. There's a lot of foundational knowledge that our students need that, yeah, AI can pump out, but we still need them to understand it and gain a mastery of it. But there are some assignments where maybe we can challenge this a little bit, right? So it's a good reflection to do when thinking about changing up some assignments. So one way that we can kind of create some renewable assignments, students create course materials. So they are creating supplementary materials, discussion questions, future exam questions, games, tutorials, and infographics. This is also nice because you get to reuse them. They're kind of secretly doing your work for you. But then students can also, in the next year, revise them, right? What can they do better, right? Students can publish zines, right? These probably won't show up too much, but something where students are actually producing some sort of artifact and maybe going through a peer review process, talking about thematic elements, and then distributing them is kind of interesting of an idea. A lot of the presentation I saw at the CAT conference was broad. It wasn't purely a STEM-based instructional kind of presentation. So a lot of these things are a little adaptive. Student-driven experimental study. Students can explore an open-ended project. This is scary. The last 4 weeks of my junior level physics labs are fully exploratory, and I don't know what they're going to do, and I don't know their questions and how to answer them. So it's a little scary to do, but it's also fun because they get a really authentic experience of exploring something. One of our students was able to, we got some funding to get a optical tweezer set up from Thor Labs, and she put it together. She aligned it, she focused it, and was able to actually capture a 5-micron bead with this laser light and move it around. And it's just so cool to see that. And I really got to see a nice sense of understanding, but also ownership from her as well, doing that, which was really cool. Another idea kind of with the lab and demo mind frame is to have students create labs and demos for undergraduate or lower level classes. Specifically, I'm thinking of having juniors and seniors make experiments for freshman and sophomore labs, right? But also involving them in demos for some of the lecture labs, the intro lecture labs, could really get a nice experience with developing some sort of pedagogical experience and understanding. Curated exhibits. We, as a physics department, it seems like we always have some old stuff sitting around. Some of it works, some of it doesn't. Putting stuff in a cabinet is nice, it shows it off, but students can also contextualize, right, and kind of create a little bit of a curated exhibit, even if it's just in the hallway, for passing students. So creating some sort of physical or digital experience, connecting past and present and giving context. Compiling glossaries, bibliographies, annotations, challenging those definitive terms and sources. I absolutely love the Noether unit. That's a prime example of kind of challenging some of what has been done and asking our students what can we do a little bit differently. What part do we play in this story of knowledge that we're kind of involved with? So it's demonstrating how a field of knowledge is built or rebuilt. And then Wikipedia editing sessions. I think the APS does this on a yearly basis with women in physics specifically. But having an in-class kind of writing session where students are practicing writing from neutral points of view, providing sufficient evidence, editing, yeah, I just think that's a cool idea to add in. So to recap, trying to keep this short, Open pedagogies focus on learner-driven education, equitable and inclusive policies and practices. Renewable assignments are inherently more AI resilient or resistant, simply because they require that context, they require that process to go through. They're not leak-proof, though, right? This isn't AI-proof. There is no AI-proof. But these might be a little bit more resilient for students and focusing on aspects that we want them to really understand and experience. Some reflection questions that I like to really dig deep into while going through this revision of my assignments. How do we invite students to participate in this creation of course materials? How do we provide a space and discussions around ethical decision making, specifically around generative AI? What is an appropriate level of engagement with generative AI in your course, in our field? I don't know if we have a good answer on that yet. It's an open discussion. Have them involved with that discussion, right? And then how do we encourage reflections from our students in their use of generative AI in the learning process? So that's kind of my shtick. Like I said, the material I presented was adapted from a presentation, and you all have it now. So thank you.
Those of you who've seen my presentation before know I'm sort of interested in the philosophy of science, the difference between belief and knowledge, or the difference between experience and reality. And so I came up with this great idea for a way that you can demonstrate Occam's razor, which we were sort of talking about the philosophy of the scientific method earlier in the year, using optics. And then it occurred to me, first of all, that, and I made the whole presentation, but it kind of gets into the weeds. You'd probably run me out of the room, and nobody's doing optics now, so that's not a very, okay. So instead I'm going completely the opposite way. I thought something to do with kinematics, and it's so elementary, you might still run me out of the room, but for the opposite reason. So this is just a little game that I've come up with for estimating the speed of cars on the expressways. And what I would show the students, if I were going to do this, is like average velocity is displacement over time. And so the distance you travel is your average velocity times the time. And if you have two cars going the same distance, then the one that's that's going the slower speed is going to take a lot more time, and the one that's going faster will cover the distance in a shorter time. But what's interesting is that the exact same proportion by which this one takes longer is the proportion by which this one is going faster. So what I do, I'm going home from St. Joe's on I-76 late at night, and I see somebody flying by, and by the way, I speed on the expressway, but only like 60 to 55. So I am like the slowest person on the road in the slow lane.
You're the problem.
I am definitely the problem. Because I don't speed enough. But I'm in the slow lane, and I see somebody in my rear view mirror just flying up, and I'm kind of curious, how fast is that person going? So here's what I do. First, I make sure that my speed is at a constant speed, that's easy to do mental math on, so maybe 60, and then I hold it there. And when they're alongside me, I start counting with 0. And I count to 10, and I note where they are, and I keep counting until I'm at the same place, like they're next to that guardrail or that pothole or that side. And I keep counting until I get it. If it takes me 13 seconds, then it took me 30% longer. They're going 30% faster. And 30% of 60, well, I don't do 0.3 times 60 this far. So 3 times 6, 18. So they're going about 18 miles an hour faster than I am. So I figured, oh, they're going about 80. It's really fun and easy to do. And by doing that a lot, and I've never done an independent check, I just think, yeah, that's probably pretty close. They're probably going close to 80. And I believe that it works. It doesn't work so well If you're on a curve, of course, because we're covering different distances, only really reliable on a straightaway. I've never used a radar gun to check and see if my gun works. But that would be an interesting, extension to the lab for the reader to try, right? As they always said in college, like, in a college text, like, the proof is up to the reader. So I just made another danger about being a physics teacher is if you come up with an idea a week before you implement it, but the rest of the week you're enhancing it. So I had to make a PowerPoint. So I see a car coming up behind me at a high speed, I adjust my speed to something simple, say 60 miles an hour. When that car is alongside me, I start counting with 0. So there's 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. At 10, I note the car's position. I keep counting, 11, 12, 13, until I reach the same position. And I think, well, 3 times 6 is 18. If I was going 60, then I'm going about 80. Why? Because it took me 30% longer to cover the same distance, so he was going 30% faster. And so that's just fun to do on the highway. And it's a presentation I can do in under 7 minutes. But if they're going really fast, and I have had this happen, if I count to 10, they're out of sight. It turns out, of course, you don't have to count seconds. You can count at any rate. It makes no difference.
That's Bill Burner.
That's Bill. I was going to say, Bill, this doesn't work so well for judging the speed of somebody you fly past. Only if you're the slow person.
I think we got to work on that.
Yeah, we could.
I've never had that experience of somebody passing. What is this passing?
It doesn't really matter if you count seconds. You can count to 10 really quickly as long as you keep the same rate. It doesn't matter if the other person is changing their speed as they go, speeding up, slowing down, you're finding their average velocity. It doesn't matter if your speed varies.
He's probably calculating how slow you're going.
No, it's not calculating.
But what you could do, and what I've had to do in some cases, if they're going really fast, just count to 5. And if it takes me 7, then it's 40%. That's simple enough. So just count to 5. And the other benefit of this is, it's very low tech and it's entertaining when you're on the road to get an idea like that person's really going fast. I wonder how fast, and you can really come up with a pretty good, I believe, not checked independently, a pretty good estimate. And then you can become sort of aware of what speeds look like. And when somebody goes by and you're like, they must be going 100, and you count and you get an idea. And I did have one case where my wife and I were driving back from Michigan, and somebody flew past me so fast, the expression took your breath away? It literally made me go, gasp. And before I could even start counting, they were gone. I didn't see the color. I think it was red shifted out of the visible. I didn't see what kind of car, and I'm convinced they must have been going like 150 or something else. But really, it is kind of cool to gain such an intuitive feeling for the speed of things. So
we're going to waste some ride those cars.
All right, so I'm Jeremy Carlo from Villanova University. So the genesis of this presentation is I was kind of surprised to discover that online you can find literally minute-by-minute timelines of what happened during the Apollo 11 mission. Down to every little anomaly and every little thing that happened. And there's also detailed maps of the route that the astronauts took on the lunar surface. So I thought this would be a great way to have sort of a kinetic adventure to recreate certain aspects of the Apollo 11 mission and also explore some of the physics. This is something that you could do maybe like a 20 to 30 minute demo. It could be an hour or more, depending on how much detail you want to get into. But per Ryan's directive, this will be the short version. So we'll get started. The Saturn V was used to launch this. 363 feet tall, so you can a bunch of comparisons online to how big this is. Interestingly, the stuff that went to the moon is actually in that little nose cone right there. The rest of this is just fuel. And in fact, about 3/4 of this was just used to get into orbit. Right? Beating 9.8 is pretty hard to do. Once you get into space, there's a lot of fun things you can do with ion drive and things like that that are actually very efficient. But just getting the first couple 100 miles actually required about 3/4 of the fuel. So 0.1% of the distance is 80% of the fuel or something like that. So, getting to the moon, so 3 hours after launch, and I handed out the little timeline there. I chose Eastern time, just because that's our time, I guess. In space, you can use any time zone with equal validity. Because a purist would say use universal time. If you were to make it Eastern, so we'll have an idea of what it was like to be here. So about 3 hours after launch, they fired the third stage of the rocket, and that sends them on the trans-lunar injection trajectory. That takes about 3 days. In theory, you could get to the moon faster than that, but there's two issues. Number one is your fuel costs rise exponentially with delta V, or I guess the number of Noethers, we should say. Your fuel cost rises exponentially. Also, if something goes wrong and you can't fire or do your braking maneuver, you're on a heliocentric trajectory. Bye. You're never coming back. The path that was chosen is actually very close to a free return trajectory, which, if you remember, Apollo 13 ended up having to do that because they had a failure on their rocket engine. And that would allow you to basically slingshot around using the moon's gravity, bring you back to the Earth. So there's a lot of interesting orbital mechanics that you can talk about here. So here is the part that actually went up beyond orbit. So each Apollo craft had 3 parts. There's this little conical piece, which is the command module, which is where they spent most of their time, about 8 days in total. It's also the only part that was rated for re-entry with heat-resistant tiles. Down here is the service module, which is basically just a big rocket, had some fuel cells to generate electricity. And then down at the bottom here was the lunar module, this gangly-looking thing. So at some point, they jettison this cone, and then they had to do something called transposition, docking, and extraction, because they had to get from the command module to the lunar module. So that involved separating the pieces. They spin the command module around and rejoin them. So now there's a little hatch at the nose cone there, and then they can use that to get into the lunar module. 3 days go by. The lunar module separates. Well, first, Armstrong and Aldrin get into the lunar module, close the hatch, very important. They separate, and that begins the roughly 3-hour descent to the moon. This was now July 20th, around 4 p.m. Touchdown on the moon, and of course we hear... Not yet.
Not yet.
The Eagle has landed. All right, so then they spent 6.5 hours on board the LEM, preparing experiments, just making sure they survived the landing. And most importantly, they were waiting for prime time. About 10:30 on the East Coast, 7:30 on the West Coast.
Oh, wow.
And it was at that point that Neil Armstrong says, "Hey, Buzz, what's that over there?" And makes the beeline downstairs. So Armstrong begins stepping out onto the moon. So there's some interesting physics here. Obviously, you're dealing with 1/6 G, so everything's a little bit funny. Big spacesuit. You've got a visor, which restricts your vision. A whole bunch of stuff around here, so when you look down, you can't see your feet, which are in these giant, moon boots. And of course, if you rip your spacesuit on something, you die. So, no pressure.
Right. Literally.
We did a little reenactment of this at Fort Washington State Park. Actually, the spacing between the legs on the LEM is 22 feet, so that's 7 or 8 paces. So you can actually see how big that is, and roughly 20 feet tall. The base of the LEM is about 1.5 meters above the ground. They needed big, long legs because they weren't sure how deep they would go into the ground, and also have some shock absorbers. There's a little bit of physics in there as well, because you don't want to. That wasn't a very convincing thought.
Use the back.
Yeah, here's the back.
They were prepared to launch it off the lead with they didn't know I saw.
That's true. So that they were prepared. Yeah, so we decided to do a little reenactment. We found a jungle gym that was just about the right size. So here I am doing my Neil Armstrong impression. Climbing down, load testing the steps at 200 pounds. And of course, when Armstrong's foot touches the ground, then we hear... One small step for man, one giant leap for mankind. And of course, you might say, well, how did they get that picture? Who was there? Well, there was a little camera that was mounted towards the base of the steps. There's a little switch that Armstrong activated. That turned the camera on, so when his foot touched the ground, that was captured by the camera. So the first thing Armstrong does, picks up a soil sample. This is called a contingency soil sample. Puts it in his pocket. Obviously, if they had to hightail it back onto the LEM, they would at least have something to show. Next thing he does, he goes back, he disconnects the little camera, In space, every pound counts, every ounce counts. So if that camera can do double duty, you may as well do that. Of course, then at some point, Buzz Aldrin joins them on the surface, and the most important thing was planting the flag. Our props budget was a little bit limited. That's what we had.
So these pictures prove that it was faked.
Yeah, right, exactly. We were able to reenact it. You can see how convincing it is.
And how come that flag is not horizontal and waving?
We'll get to that. Yeah, so the flag was planted 27 feet from the LEM, which is about 9 paces. So you can have someone go 9 paces, put down the flag. Of course, there's the real picture. This was taken by Armstrong of Buzz Aldrin, saluting the flag. Is that my
2 minutes, yeah.
All right, we'll get there. Now you might ask, how's the flag waving? Well, there's actually a little bar across the top which holds it up. Interestingly, one of the subsequent missions, that bar failed. So the only picture they have of the flag, one of the astronauts is holding it up. Otherwise, it would just be hanging down limp. The other missions also put the flag further away, because when they took off from the surface, Aldrin reported that the flag was knocked down by the rocket exhaust, which is not a good look. Toppled over flag. Also, the flags are probably white by now because of the UV radiation, so they'll assume that we arrived and we surrendered. So a little bit about the what was known as the Apollo 11 traverse. So they've actually mapped out the paths that the astronauts took. So the first diagram that you'll see on the back of your page shows some of the topography. So there's the LEM, that's where the flag was planted. Then there were a couple of experiments that I described a little more in the handout. There's a solar wind collector, basically a big piece of fly paper. There's a passive seismic experiment package, basically a little seismograph. And probably the most important was the lunar ranging retroreflector, which is a retroreflector they put on the surface, and it's actually still used to this day, bouncing lasers off it from the Earth to determine the distance of the moon to within centimeter precision. The largest distance that was traveled was actually about 200 feet. Neil Armstrong went to the edge of this crater to take a panoramic photo. And in fact, all of these Pan 5, Pan 4, you could find those online, that they're all labeled. In fact, there were still photos that were taken as well. Here's a kind of a stylized version that shows the paths a little more clearly. You can also find online comparisons to baseball diamonds, soccer fields, football fields, and so on. So here we are. We tried to reenact the 200-foot maneuver. So that's about where the LEM was in relation. So then they retired to the LEM for the evening. So in all, the EVA was about 2 hours and 15 minutes. They were on the surface about 21 hours, so most of that was spent on the LEM. Subsequent missions spent more time outside, I think up to about 7 or 8 hours. Of course, the final 3 missions also had the rover, so they were able to go quite a bit further. But for the first mission, they were very conservative. They didn't want to go too far away, and they didn't want to spend too much time outside the LEM. So anyway, they started returning. So interestingly, again, in space, every ounce counts. So anything that they didn't need for the return mission was left behind on the surface. Any tools, other equipment were left behind. Of course, remember Alan Shepard brought the golf club. That was left behind. Apollo 15 had the hammer and the feather. Remember the Galileo demonstration? Those are on the surface of the moon. That's just what I was going to get to. So, collectively, the 6 missions left behind 96 bags of human waste. Because you got to go, you got to go. So what did they do? They bagged it up, and you don't need it to get home. So they did the most American thing imaginable. They left it there.
You can't do that in a national park. You got to bring your bag home.
Didn't they at least dig a hole? Left the bag?
And there actually was a proposal to go back robotically and to retrieve some of this stuff to see what the effects of radiation were over the 50 years.
You have to care about dogs.
Yeah.
There's sentient shit on the wall now.
So here's re-entry. Of course, they splashed down in the Pacific. They were retrieved by the U.S. Navy. And then, of course, began the most interesting part, the 21 days of quarantine, which probably was unnecessary, but they didn't know at the time. So if you have any moon landing deniers, 50 years later, the Lunar Reconnaissance Orbiter imaged all of the Apollo landing sites. So you can see the descent stage of the LEM, that's the legs and the platform. That was left behind. You can see some of the experiments that were left there. And a few of the others, you can actually still see the flag, but they've actually verified that it's still, at least the pole is still standing. And if you want to see the command module, it's in the Air and Space Museum, right near the Wright brothers plane. So kind of an interesting little adventure that you can do with your students or any other group. You can choose what you want to focus on, how deep you want to get into the physics, how many details you want to go into. I left quite a bit out. This is the short version. There's a little bit more in there. And if you want to try to recreate it, you can try that.
The Franklin Institute has a full-scale model of the lunar landing module.
Okay, so you could actually see it then.
In the play yard out where there's all of these different climbing structures, but then there's this full-scale model of the lunar lander as well.
Yeah. Ron.
It's also interesting to point out that all the pictures of the Earth and Moon in these kinds of diagrams are wrong. The Moon is 30 Earth diameters away from
the
Earth.
scale is off.
So if you look at that first picture and go 30 Earth diameters away, that Moon is a long ways off.
Yeah.
Long.
I remember.
There you go.
See it in demo 13.
Yeah, just as an aside, if anyone ever gets to Houston, the tour at the Johnson Space Center, they actually redid it for the 50th anniversary. You can go in and see. They have docents there. People are actually there for the moon landing. It's all reset up. You can see it. In fact, it's fantastic. Well, even if you go to the mission control is opened up, you can actually see it. It's fantastic. Bucket list stuff. Really is.
If anybody wants to do a lab where you have your students measure little G on the moon, I can point you to a clean film clip of the Commander Young jumping from that clip with a good time base, so you could use a video analysis program to measure little G on the moon.
Hey, Bill?
There was I thought, a really interesting thing. One of the subsequent missions, they were pulling a cover. They had a foil cover on something on the base of the LEM, pulled it off, and the astronaut tried to throw it to the side. And of course, you don't have much mobility, so he had to throw it almost like a shot put. He had to move his whole body. And he had forgotten the difference between weight and mass. And that backpack is 200 to 300 pounds. But of course, on the moon, it only weighs about 50. But he forgot it still had all that inertia. And it knocked him down. Like he spun down because he didn't realize that. And they had a protocol to get back up. But that would be an interesting thing to get into that weight-mass distinction.
I used to teach in Florida, and the Saturn V rocket is in Cape Canaveral. I saw it, and it is huge.
My name's Matt. I'm a physics teacher at Great Valley High School, and when the call for this meeting went out and no demo too small, I'd say I'm going for the very low bar here. I'm going to save you 7 minutes. I have never actually pulled off live the demonstration of the fine table setting with the china and whatnot, where you remove the tablecloth from underneath, right? But we have the next best thing. Of course, you would take a nickel and you would place it on top of that paper, and if you slowly move that around the table, you could argue there's a contact interaction between the nickel and the paper, and that contact interaction will be parallel to those two surfaces, and you might call that, well, static friction. Or if you were to quickly pull that paper from underneath, there's a different kind of contact interaction also between the nickel and the paper, which will be parallel to the surfaces, and that would be kinetic friction. Well, it's not impressive doing that on a table. What would be impressive is if you could do that on the end of your finger. Now, to take your two fingers and try to withdraw that from underneath, that's not overly impressive, but if you flick that from the side, so if you ever need 5 or 10 minutes to fill, having 30 kids, send these across the room simultaneously is worth it. That's my day.
So anyway, apropos Chris's talk, long before AI and long before ChatGPT and students developing their own materials, I had an education student in my lab for a summer, and I tailor-made a project for him. And what he did was he looked through the previous 10 years of physical review letters, and he found a bunch of papers that could be modified for some benchtop experiments. And we published that in the physics teacher. So this is long before that, but that was it's fascinating that we're moving toward doing those kinds of things. So I'm going to talk about friction and adhesion, but in a weird way. I heard that Bill Berner was not going to present today, so that opened up some things for me to do a Berner-esque type talk. So anyway, does anybody know who this character is?
A guy.
That's Eli Whitney. And so we know Eli Whitney is responsible for A, inventing the cotton gin, and B, incorrectly given the title of the father of American manufacturing. As far as the cotton gin is concerned, he spent most of his time with the proceeds of the cotton gin fighting infringement, because the cotton gin was such a simple device that people were replicating it and selling it, even though he held the patent. But he really, as far as interchangeable parts were concerned, he was more of an advocate as opposed to the inventor of the idea, because it really predates him. It goes back to the Punic Wars, right? So, but as far as American history goes, right, he's touted as the quote-unquote inventor of interchangeable part manufacturing. So what was really required for interchangeable parts manufacturing were length, and in particular screw standards, right? So, before Whitney, if you had a musket, and it broke, right, that your musket was a one-off, and you had to go to the local smith and have that part remade, and couldn't just go down to the local store and buy a replacement part. So this sort of getting standardization of length, and especially screw threads, which I'm not going to talk about today, right, ushered in this whole science of metrology, which we still, the National Institute of Standards and Technology is totally responsible for, okay? So also there was, even though there were some length standards at the time, here's the Imperial Yard, circa 1825, there were no portable sets of length standards that can be used in, the machine shop at the end of the block, right? So, and that was a problem, all right? Because then, what I construed to be an inch might be close to what someone else construed to be an inch, but it could have been off by quite a bit, okay? So along comes a relatively obscure inventor. As a matter of fact, if you go to C.E. Johansson's Wikipedia page, it's no more than 2 or 3 paragraphs long, okay? And so what he did, he invented what is called a gauge block set, okay? And I have a couple of these. This is circa 1920. And so it's a set of gauges that go from .1001 inches out to 4 inches. And these are standard length blocks, such that if I had a set and another machine shop had a set, then we would be talking about the same length scales within 50 to 100 nanometers. That's how precisely these were made. And they came on the market in, well, quote-unquote market, 1899, invented by C.E. Johansson. And so the first gauge set in America was sold to Henry Leland, who was the CEO of Cadillac Automobile. It's around 1908. When you really think about this, it's really not that long ago, right? We're talking about 100 years ago that these standards were beginning to take hold in manufacturing process. Okay, so Ford bought the American company in 1918. And if you come up here, you'll see Ford Motor Company engraved in this Bakelite box. Okay, so this is, again, from the 1920s. And there it is. It's an 81 set piece. You can still go on eBay, and you can get a set like this for, a couple of $100, right? It's really pretty cheap. So Johansson also responsible for the standardization of the inch. So the inch in the US and the inch in the UK differed by about 73.8 parts per million, okay? Millimeters. And so what he did is he nominally chose a length of 25.4 millimeters, 2.54 centimeters, as the standard industrial inch. And as it turns out, right, in 1959, the International Yard and Pound Agreement fixed the inch at 2.54 centimeters. So when you tell your students, right, that 1 inch is 2.54 centimeters exactly, this is the reason why. Okay? Which I honestly, I think about that all the time. Why 2.54 centimeters to the inch? Okay.
So sig figs on that.
What's that?
How many sig figs on that?
This is exact. It's a definition of the inch in millimeters.
This thing is exact.
It's exact. So it's 2.5400000000 millimeters to 1 inch. It's a definition. So now what's so important, right, because I haven't mentioned friction at all yet, is that these gauge blocks, they exhibit the phenomenon of what is called ringing, okay? So if you clean the surfaces and you come in and slide one against the other, okay? Whoops. Yeah, it's not going to do it now. Damn it.
I saw it happen earlier.
Yeah.
There's a jar up there.
There we go. So they will ring together. And you can see here, these are old blocks, so they've been around the block a few times. And so here's Johansson holding, a fair number of blocks. They're not magnetic. There's no glue. Okay. So what's holding them together? Right? That physics is still not well understood. So there was a demonstration, right? Johansson used to go to conventions, engineering conventions and shows, and he would demonstrate just how powerful the interactions are in this ringing. Okay, so here you have 50 kilograms, over here you have 200 pounds. It's roughly the same. And if you calculate the force, right, just gauged on pressure differential from atmospheric pressure, you get around 31 newtons, okay? And you know that that's not even close, right, to overcoming the gravitational force. This is 100 kilograms, right, which is about 1,000 newtons, okay? So you've got differential pressure difference, 31 newtons, ain't nearly sufficient to accommodate the 1,000 Newton gravitational force. So what is responsible for this? Okay. Well, there's still not a lot of consensus on this. The possible reasons might be van der Waals or London dispersion forces. Some even claim that the Casimir force might be responsible. There might be a fine lubricating layer between here that you can't clean off. That might be partly responsible. Atmospheric pressure differential, which I just showed you a sample calculation, cannot be sufficient. And you'll notice that in order to ring these together, I rubbed the surface with a fair amount of friction between them right? And some people suspect that what I'm doing is cleaning the oxide layer off the steel and somehow having the steel layers, right, come in very close contact, right? One might call that a cold weld, okay? So no one really knows, okay? There's probably lots of little experiments you can do, right? You can buy single gauge blocks online, right? It might be 10 or 20 bucks a piece. You can actually have them, machined at the end, and your students can do some experiments on how much weight they can sustain, and talk about like what the possible reasons might be. Bill?
Is the load that you have there perpendicular to the joint?
Here?
Yeah, like when they're hanging the weights off. You would turn
so that we'd be this way.
Vertical.
Yeah. So it's under tension. Yeah, absolutely. Geoff.
Do coins involve cold welds, like when they make layers of coins? They're not like really, are they pressed together such that they?
Yeah, I'm not sure actually, right? So, yeah, I know if you get two metal surfaces really close together for a serious length of time, there will be diffusion of atoms across that interface. Yeah.
The challenge, of course, is getting our students to understand that velocity is relative. I've been for years showing the first 8 minutes or so of the PSSC film from 1960 on reference frames. Provides a good 8-minute nap for my students. It's ineffective. Okay, so I built this over the summer, so I haven't used it with my students yet. I don't know how it works. It's a Pasco track, and the Pasco track is sitting on 2 of these. The standard constant velocity car, and we have a third one, and there's a wireless position sensor on the top, and we're going to measure the position versus time of the red car with the position sensor, and then I'm going to ask my students to tell me what the velocity of the car is. Are we ready? Yeah, but I have to pick it up and start the motors first because the floor is very far away.
Jeff, do you mean the Toronto frames of reference video? Or
Yes, the frames of reference video, yes. The PSSC frames of reference video. Wonderful for us to understand what's going on.
My father worked there. He had those professors of physics.
Only Laura.
I did this last night with most people in the room.
Laura, you have the best seat in the house.
I know. Ready? Okay, go on.
3, 2, 1.
Oh my God. Nice, very nice.
So I wonder if, do you have to use, if you're using the constant velocity cars, do you have to use a track? Or can you use like board? That's fine.
So you need 2 pieces of information, right? They see, using the line on the floor, that the car is not moving.
Yes.
So its velocity is 0. But they see, using the motion detector, that position versus time is a beautiful straight line. So clearly the car has velocity. So they have to answer the question, what is the velocity of the car?
In my course, I teach a sequence where I go kinematics, forces, momentum, and then I go circular motion, gravity, and energy. So I was looking for a way to bring back the Orbit of Mars lab, where you map out the orbit of Mars based on the slides. But the last time I did it, it took 2 days on block scheduling to get data, and it was horrible. So that was 180 minutes for something that wasn't worth the squeeze. So I went online and found data on the 3rd page of this packet that gives you the position of the Earth in a circle and the position of Mars on those dates. So between that, you'll plot 8 points on the graph paper on the last page where you can actually get the orbit of Mars. Mark where it's near, mark where it's far, and basically get an orbit of Mars done in about an hour, as opposed to, a couple hours, which is what it was taking when I did the Orbit of Mars lab before. So then I asked questions that would serve to wrap up those units. So to use this as an assessment in a way to link circular motion, gravity, and energy, and to pull the concepts out where they can do that, leave the day before Thanksgiving when I'll be doing this, and have a sense that they've actually linked those 3 units together. So I wanted to share this with you guys before I put it in my format, where it'd be more for my students. But this is the idea where they'll be able to plot that, and those that are teaching AP1 with gravity can actually use it, and those that are teaching with energy can use it. The point is that I thought that would be useful far enough in advance of when you're getting to those topics that you can modify it, whatever else. If you do want the Word document of it, just email me and I'll send it to you. The bottom line is that you should be able to plot that 8 points. You should be able to get a sense of what the orbit looks like and be able to use that. So whatever you guys need. I just wanted to share this with you because the Orbit of Mars lab is a great lab when you have the time to do it with the pictures. It's just no one has the time to do it. So anyway, that's all I wanted to share. So that's it.
Hi everyone, my name's Alyssa. Hi, Laura. Hi, Paul. I teach at Springside Chestnut Hill, all levels of physics and astronomy and a little bit of robotics engineering. So, if you're at the last demo day, you might remember my 5 demos for $5. It was like Pizza Hut. I'm back with 5 more demos for $5. To be clear, each demo costs about $5. So Matt's got the cheapest demo of the day. His is like a little over a nickel. But each of these is about $5, and they're not, so because of the price, they're not like the most mind-blowing, like I'm not coming from Penn with the most expensive 400-year-old machine. No hate on Penn and the 400-year-old expensive machines. But my goal is that I know that everyone in this room will have probably seen one of these. You've been teaching for months, so like I might get you on all 5. But if I can get everyone in this room to see at least one demo that they haven't seen, I will do my best. So we're going to start with a really basic one. We've talked about the Earth and the Moon. This is a meter stick, binder clips. These are like cocktail skewers. I found them in a closet, and this is clay that I baked in the oven that I took from my daughter. So actually the cost of this was free. If you don't, I did buy the clay for my daughter. She doesn't work. But she's 5, that's why it's funny. These are scaled correctly. So the moon, like that's why I made them out of clay. They're not like little toys. I actually scaled them and scaled them to the meter stick. I have apogee and perigee marked. You can shine a flashlight over here and be like, look, eclipses, annular versus total, and it's just cute to give the scale. If you aren't a fan of fractions or just want the spreadsheet, I have a spreadsheet with this, but for the whole solar system. At this, I have it at this scale, and then I have it at the sun as a basketball scale, which obviously would be much, much smaller. I'm happy to share with you the spreadsheet if you don't want to make your own. Okay. Let's see. This next one is a oldie but goodie. These eggs are raw, but they've been in my car for 2 days. So they're not, you guys probably know what I'm doing. So I have some raw eggs. They're like this is, sorry Kathleen for your classroom. And I have a sheet. You can get a sheet for under $5 at places such as Target. So we're still under $5. Who here has not done, because I'm going to make you help me, who here has not done the egg and sheet momentum demo? Let's see. Great. We're going to take you, I need 4, and the 2 of you. Could you guys come up? We're going to do it inside, and I'm going to show you guys how to do it inside. That's for the rest of you, I'll show you how to do it inside. So I'm going to take my 2 taller people, and I'm going to put them in the back, so that's going to be you and you. And if you guys could hold the sheet up just like this. And where I'm doing this is in my momentum unit, and it's on the day that I've introduced impulse. I'm going to have you guys take a big step forward because I don't want that cabinet behind you. And you guys on the bottom, you're going to kind of crouch down, and our goal is to have this up really high but have like a nice view right there. Because what we're going to do is you're going to take this raw egg, and I'm going to pick whichever child in my room is a softball or baseball pitcher, and I'm going to have them throw this egg as hard as they can at the center of the sheet. Now, notice I let them step forward. You don't want something behind it. In fact, step forward again. I'm just really nervous about that desk. And hold it up nice and high.
I use a fitted sheet, so it's going to roll down.
That's smart. This was like some
That's more money.
that retired. Yeah, let's do $2. Yeah, curve it up. So my people at the top, your only job is not to flinch and drop the sheet. My people at the bottom, your job is to make sure the egg doesn't roll off, because guess what it's going to break. Who else hasn't done this demo?
Okay, timer and Walker, do not miss the spring.
Oh, time Walker, we have to use Kathleen. So, and he's an athlete. What's BS?
Sidearm. Don't miss the sheet. Don't miss the sheet. It could be really close.
That child, you're like, you're the pitcher. Like, who are you? And you're gonna get someone else to be like, as far you can do as far as you want. I've never had a kid break it. Oh, that's cool, right? Thank you so much.
You're going to show, hey, I'm tiny.
No.
And then the next step.
Just be careful if you have a softball pitcher too, because one time I had a girl who did
So what I do next is I have the kids throw it at the nearest tree. So if it's nice out, I take them outside and we actually chuck it really hard at a tree. And then you put the equation for impulse on the board and you're like, what is changing in this equation? Why did it break so easily in one? Because they're like, it's hard boiled. And you're like, first of all, a hard boiled egg would not survive that. But that's egg and sheet, great for impulse and momentum. I do this with 9th grade, and you can draw like, look, like the T is going up, and if the J is constant, what, that type of thing. Okay, next one. This one is going to require a volunteer also. And my promise to you is that I Lysol wiped this ahead of time. So this is a 3-volt motor. I got it off of the internet. Those of you that were at my workshop / COVID super spreader event this summer, you guys got to build these. Yeah, come back next summer. We're gonna have like whatever the new variant is. We're gonna have like, and it's soldered.
We were inoculated so that now we're not going to get
Guess
it.
who doesn't need COVID shots this fall? All of the attendees. So November 1, that's when we get them. So I have soldered this to an audio jack. Learn this the hard way. You have to make sure it's mono. It has to be single channel or it doesn't work. You also need a dumb enough device. Some devices won't send an audio signal. They're looking for the chip in the headphones. So weirdly, it doesn't work with my phone and a converter, but it does work. This is a brand new MacBook Air and it's not smart enough to be fooled. So I'm going to play music through this and you're going to hear nothing ideally if it actually goes through. I have BTS queued up. Great. You hear nothing. But you can feel it. Okay, I'm going to need a volunteer, and I'm sorry, but I cleaned it. Is anyone willing to put this in their mouth? Great, come on up. So, here's what we're going to do. First, I'm going to have you hold it, and I want you to just feel the motor. What do you feel when you hold it? You don't feel anything? Here, I'm going to pause the music. Oh, now it just starts. Okay, what do you feel? Now I feel a vibration. Yeah, you feel a vibration. We talk about what is sound. So this is a sound demo. What is sound? Sound is a vibration. And then what I'm going to have you do is see the motor shaft here. I'm going to turn it on again. You're going to bite it between your 2 front teeth, so that your front teeth just pinch there. And then you're going to plug your ears. So just bite the shaft of the motor. I do this with a sanitizing wipe, by the way. So what do you hear? That's amazing. Yeah, you hear BTS. What do everybody else hear? Nothing. So this is a good demonstration. This is how bone conduction headphones work. It's forced vibration, not resonance. You can also have kids make these for about $4 each, which is pretty cool. Okay, next demo. Yeah.
What happens if you just hold it at the bottom of a paper cup? Does it make enough of a speaker that they could hear?
Let's find out after this.
It'll work. Yeah.
Maybe. I don't know.
I did this once with a tongue depressor and hold a bunch of speaker wire around it. I put the speaker wire into the speaker jack, then on the tongue depressor and put a magnet around the coil.
Sure.
And then with enough coils of wire, the students could come close and listen to the music off of my jaw. And it was deafening inside of my head. And they were just like, oh, I think I can almost hear it. Yeah, that's cool.
You know what, I'll try it in a minute because I don't want to hit my 7 minutes too hard because I still have 2 more demos. We're still under $5. So this is probably not like a new demo to a lot of you, but I made it a lot cheaper. This summer I was at a workshop and they had this Doppler effect demo that was from Pasco and it was just tremendously over-engineered. There was a frictionless bearing and a switch and a bar. There was a lot going on. So I went home, took a buzzer, put it on a battery, put it on some rope.
Cool.
Boom, Doppler effect. So this is just one of the 3 to 6 volt buzzers. You could add a switch. Laura made one this summer and added a switch that's much nicer than mine. You can also put these in like a Nerf ball and chuck them across the room. You can just walk across the room. But there's a lot that you can do. I'm not swinging it by the cord for obvious reasons. I have nylon rope braided into the cord. That's the like.
I was going to say, you took all the thrill out of it. Put the battery out where it gets swung around so there's some possible damage.
We may have tried that over the summer.
Not on purpose.
Not on purpose. Somebody may or may not have soldered something backwards.
Yeah.
And it was interesting.
It's not what we wanted.
And it went flying.
At the center of the circle, you won't hear the Doppler.
No, I don't hear anything.
And I asked the student, I don't hear it. Why is that? And one girl said, because you're old.
That's not
So they can use it in biology class.
Wow.
You can't hear their
Here's my last one, and this is the one where I think I'm going to get you. I know there's probably a few people in this room that are like, yeah, I've seen all those. I got you. Okay, so this is credit to the Perimeter Institute, has anybody been to one of their workshops? Damn it. Okay, but this is from them. But have you not seen any of these?
Keep going.
Okay. Okay. So what we're going to do is we're going to talk about an object being dropped at rest in free fall. And I've plotted out time and position. So like we drop an object, boom. And you could do this with the kids. You can plot this and we get a little plot. I have it in tape. I have my position. I have my time. I did do this with a ruler because I initially didn't. Showed it to my co-teacher and they're like, you can't go to physics teachers without a ruler. So here we go, and we have a curve. And what you can do is you can say, okay, if we had an object dropping, but we also had an object stationary on the ground, you can plot it compared to that. It would just be, like along the axis, and you can be like, look, an object at rest is at rest in a straight line. An object that's dropping follows a curve. What does the curve imply? The curve implies acceleration. If I were with AP, I would be like, what is the derivative relationship? With your big kids, you can get into more than just a curve as acceleration. But right now we are talking about an idea of free fall, an idea of gravity. That is, that gravity is an at a distance force acting on this object, pulling it towards the Earth, and it is accelerating because F equals ma. That's not like super what's going on. It's not accelerating because F equals ma. It's moving through curved space-time. So what if we were to put this axis on a curved surface? So here I have the same xy axes, and as a tip, you do have to shift the x-axis above the equator of the ball, or you end up with a straight line. It doesn't work. I saw this done with yoga balls, and it was bigger, and students actually plotted on it. I plotted on this ahead of time because I get 7 minutes. I'm already at like 9. But beach ball is what fit in my bag today. And you can see that when you plot the same thing, we end up with curved axes, and we end up with a straight line. And you can do this with tape, and you can see that the tape lays straight across this, whereas the tape, if you go across this one, is curved. You end up with crinkles in the tape. Here we have straight axes and curved tape, and we would get straight tape for something sitting still. Here we have curved axes and straight tape, and you would get crinkled curved tape for something sitting still. The object sitting still is the one that's on a curve. The object that's moving, that's in free fall, is moving in a straight line along curved space-time. So this opens up the door, depending on what level you're teaching, this opens up the door to just talking about different conceptions of gravity, or like inertial reference frames and relativity and all sorts of things. So those are my 5. I do have a quick bizarre plug. I like to follow my things with a quick bizarre plug. I'm working on a project right now that we are in the active recruiting a couple of local collaborators phase. There's no Drexel people here, right? Why doesn't Drexel come? But I'm working with Drexel. We are putting muon detectors on high altitude weather balloons. So if you have prior experience with either of those, and if that sounds like something that you're interested in, come find me afterwards, because we are starting up something cool. So thank you.
So we wrested some money out of the school. to hire 2 high school physics teachers every summer. And whereas I benefited from being there for years upon years and sort of hoarded that resource, we're now mandating that 2 years you move on, 2 years you move on. So every year we hire a new high school physics teacher. This is a plug. If you know anyone in their first 5-ish years of high school physics teaching, we haven't tested the bounds of that time limit because we've been lucky enough to find people in their first 2 years, which is ideal. They come teach with us in July, and this was the product of us sort of going into my workroom and developing curriculum. So they planned their first kinematics unit alongside us in the summer, while they're also seeing lots of other physics topics taught at a dizzying pace. Anyway, so I'm just so proud of these guys, and like I say, I don't know, we might have a hard go in a year coming up soon because the bar's been set so high. Anyway, so Alyssa, you did get me with that ball. And speaking of the summer program, I teach general relativity every July. And before you were done talking, I decided that was part of my talk next year. So I've got something that is, if hard pressed to say what my favorite demo is, it's got to be this one. It's so ridiculously simple, but it's so deceptive because it's an amazing lab on 2 fronts that kids should be doing in your room. Any sort of linear, massive thing that's not perfectly isometric, right? Like it's got some irregularities at each end. If you start with 2 hands supporting it near the ends, if you slowly start to bring your hands together, what do you see happening? The right hand was slipping. That's not happening anymore. Now it's my left one. Now it's my right one. Now it's my left one. As you bring the support further in, this is more weight that's out over the end of that support cantilevered, right? So you have a bigger torque on that support. So therefore the friction is more. But it keeps alternating back and forth, which one's getting the greater of the friction in that dynamic event. And 10 times out of 10, 100 times out of 100, you will find the center of mass for that thing. It's as simple as that. And talk about bucket lists. Have you not been to the Louisville Slugger factory and gotten your own name printed on a Louisville Slugger?
Not yet.
Where's it going to be on this one? Way more to my left, to your right.
Sweet spot.
Sweet spot. Center of mass.
Necessarily the sweet spot.
Yeah, I was about to say that too.
The sweet spot is the center of percussion on baseball.
That would probably be the more in the middle of the barrel. Anyway, it's, I've done this, and then kids just get up and start testing it with brooms, literally anything they can find for the next 15 minutes.
You can do it with
you can do it. You can do it with that. You can have 3, and find the center.
I discovered that as a waiter.
So, 1 second.
By trial and error?
So,
how many meals were lost?
Yeah. Geoff's rotation thing is also one of my favorite things to do. And if they're concurrent in their geometry class with you, you can talk about it in terms of centroid. And on any triangle, the centroid from each side, the dividing ray that meets the bisector of the opposite side, where they all intersect is the centroid. That will always be the center of mass on a triangle that's isometric. And you can just put it on a pin, on a finger. Anthony.
I use a plunger. Get 2 plungers, or you just get 2 bats, and then you cut the bat where it balances.
Don't cut that bat, please.
And then you ask kids which half weighs more. And that's very counterintuitive. I'll try to bring that for a future show.
Did you ever deliberately go really fast and mess it up?
Oh, sure. Yeah, that's got to be part. Thank you for saying that. And I said this earlier, like a little off-the-cuff thing, but it's actually serious. The non-example is also crucial to show in any demo. So the non-example would be, I didn't have time to have friction acting because I went too fast.
Can you go backwards? When you balance and then go back.
That's
if your hands go back to where they were.
It doesn't look like it.
That's tough.
I don't think so.
Never much more friction.
When everyone starts first, is going to keep going.
It's not reversible, right?
It's not reversible.
But these are all good things. But what you do in a classroom is say, this thing that we all explained in 5 minutes, that should be 2-3 days of explanation for your students. They should be developing an explanation that holds water based on physics.
Sweet.
Cool. That's me. Mary, you're up.
Right, so yes, Penn has lots and lots of very expensive toys to play with. And it would be great if we could show them in a way. This is the correct HDMI cable? Yes?
That works for me, yeah.
And it would be great if we could show those in a less expensive way. So what I brought along here is a gravitational lens. The curve, and I think, does Penn have the only 2 of these ever?
Well, I mean, Bognish worked out what it ought to be. You know, it's some hyperbolic curve that we then machined and flamed, and, you know, some other folks may have done it, but Penn built their own from scratch.
Wow. Right. And so you're all welcome to play with these and get a selfie behind these if you would like. There was a scavenger hunt at Penn where they were like, find the giant lenses. And so I had to pull them out for these students, and they all went to take selfies like in front of it instead of behind it, and that was mystifying
So
to me.
like a quick clarification, this is an optical analog to what a gravitational lens would create. In other words, if, you know, because we can't get enough mass in the room to make this work, so.
Right.
We'll change the index of refraction and try to do the same thing.
Right, so this is, again, a mathematical approximation. This simulates what it would look like if a black hole passed between you and me, or a supermassive galaxy passed between you and me. You can download an app for this called GravLens that you can also do the same thing with. And wow, I should have brought up that picture I have of you for that. But what I want to show you here, if it's going to talk at all, which it was up for a second, wasn't it?
The projector is not even.
Like, what do I do to fix this situation? Sorry.
It's a gravitation.
Thank you for being not vertically challenged. Because it was there for a hot minute. It was gone. But all right, so before we do that, while this thing is warming up, could we shut the lights out in the room, please? We have a star shower here. And what a star shower does is Bill likes to call it a lazy man's Christmas lights. And I don't mean to put that gendered, it's a lazy person's non-denominational seasonal house lights. But so, we know what this looks like going through a lens.
Oh my God, that's so cool!
Right? Wouldn't it be exciting if we could see that? That projector's never coming on. Oh no, now it's finally coming on. So that's what the Grav lens does. And that's very exciting. And now that this is coming up, we'll keep the lights out so that we can take advantage of this a little bit more. Over here I have a picture or a video of my son looking through this. So kind of see his face on there, kind of taking that in. And this summer we decided, what if we took a look at the star shower through the Grav lens? And what you can see on it is, it's super beautiful. You can see an Einstein ring on it, right? And that's really cool. But these might be the only 2 of these that have been machined. There might be other universities that have them. So how in the world do you do that in your classroom? Well, the illustrious and brilliant Bill Berner pointed out, where did it go? That the curve of that is just about like if you had broken off the end of a wine glass. Right? And so I did this haphazardly yesterday in my lab, and this is what I got on the end. And so you can see it does a pretty good approximation of the nice fancy machined Grav lens, and all I did was break off the end of a wine glass. And so these will be here. This is not well sanded, so don't stab anybody. But it's not that sharp.
Why, you know what to do with all my wine glasses?
But yeah, so you're welcome to donate all of your wine glasses to Penn, and we will not only shatter the globe with sound, but we will also save them and keep the ends for this. But you guys are welcome to afterwards get pictures with the grav lens or look through that. Some of the things that we like to do with this are if you have a special effects, equipment for your theater program, if there's a smoke machine, one of the other really neat things with this is being able to turn this on, get the smoke machine going, and you will see where the rays of light are bent and going in weird directions, which cause this funny phenomena. Right? But so that's my, if you have an astronomy club or something like that, this is how you can bring gravitational lensing to it on the cheek.
Does the wine glass work for the star shower?
Yeah, that's what this video is. It's the star showers right behind it. You just can't see it.
No,
So just
right
1
now,
second.
right now.
Yeah. My hand might end up in the way, but shoot.
Wow.
But you see it doing, it's not quite the same because my eccentricity is not perfect.
It's still,
But yeah, and I would,
Projector sending out all those stuff, light at the same time.
but yeah, it's a diffraction grating over it's two lasers. But it's a diffraction grating over 2 lasers, basically. And Bill found these the week after Christmas for what, $2?
Yes, I think this was in pre-inflationary times. I think we got 20 of them at $5 a piece.
Yeah, Bill called me. I barely worked at Penn for a month, and he was like, "Oh my God!" And I was like, "Buy them all." And I was like, "Is that the wrong answer?" And he was like, "No, you're the right person for this job." So,
$5 for that?
This one was more expensive, but we have a whole bunch that are used in our
But they're
undergraduate
still,
labs.
these days, you can still get them, at the, as seen on TV, sale things at like Boscov's and stuff, like $30. I mean, it's an incredible ray tracer.
But yeah.
And, if you can get a smoke machine, God, you can blow people's minds. Star shower. Yeah, those are the things people have on their
An Einstein ring is what it looks like. So what happens is... I just ruined it. Oh my God, no,
yeah.
All right. What happens with...
No.
It hides. No, it's completely...
You can get them for $30. Delivered tomorrow at 4 a.m.
So what happens with gravitational lensing is if your eye is here, like this is you, this is my terrible job at drawing your face. There you go, this is you, that's your eyeball, and this is a star, and there's some supermassive galaxy or whatever out here, or like dark matter, whatever out there. The light is going to bend around this and make it to your eyes, right? It's going to follow a straight line, but it's going to bend around and make it to your eyes. But we perceive light in a straight line, so we would perceive that star, I'm so sorry, out here. We would perceive that star out here. So astronomers were seeing these 2 stars, but then when they looked at their spectral fingerprints, they were the same star. And then they were finding these smears in the sky. And then in some cases, they were finding these almost whole rings. And that whole ring is an Einstein ring. Einstein theorized that that would occur in the right settings.
Closer to perfect geometric alignment. If you actually have the 3 points in a line, you're going to get a nice ring.
A nice Einstein.
And if you start squeaking off a little to the side, you
Right, and so this object, this supermassive object in the middle here, this is your gravitational lens that's causing that phenomenon. The other thing that I wanted to tell you is, can we bring this guy up again? Sorry, because this is our announcements page, it seems. I don't want us to forget this. But also, the Penn demo shows, wow, it's been so long since I've written with dry erase marker, are going to be on January 8 through 10.
Hopefully not the Keystone.
8, 9, 10, and last year was mechanics, so this year is electricity and magnetism. So, so if you're interested, we're still working with Penn to get them to actually approve the auditorium for those dates, but I'm done with waiting until they actually approve it, because then it's November and there's no time to get a bus. So it's there, it's a free show, this year's E&M next. But yeah, I'll send out an email and I'll actually double check that my response is send.
because 2 years in a row now I've been bitten on that I'm like, oh, send, 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 and then they're like, no, you're on the train, you have no reception, it's going to go in an outbox, and we're never going to tell you.
Oh, yeah.
And so that's there, it's coming. Last year the timing was a little bit rough for, I think, middle school to be able to be there, so we're adjusting the times back so that it's easier for both middle school and high school to be able to attend shows.
Just a comment. I mean, I'd love to take my kids, but it's always at Keystones and we're not allowed to go.
I gotcha.
Keystone testing.
Wow.
Some schools will not let you go during Keystones.
Right. I didn't know Keystones were in January.
Yeah.
So they do. So it's the makeups for any kids who either have not passed them yet or who didn't take them.
I gotcha. That's good to know.
But yeah, it's usually the first week and a half that you come back. The school district goes. For the school district of Philadelphia, it's the first week and a half, that Keystone window. It's usually like the 6th through 12th or 15th or something like that.
Okay.
But I know that the Penn kids then come back
our
and the
semester
auditorium becomes
Yeah,
difficult to get.
that's the biggest problem. Yeah, I know.
Quick point about the star shower. It is a diverging source, in essence, from a point. You can get parallel rays by going out and getting one of those cheap, big magnifying glasses, sticking it in front and moving it around until you get parallel rays, if you want to do something with parallel rays. But it's not hard to get the rays parallel.
Right. I think Peter wrote an article for the physics teacher on exactly that. And so, go for it.
So this is a list of all the demos I'm going to do with various websites, things like that. This is my mechanics teaching sequence. It probably is similar to yours. I do motion, projectile motion, they're the same. Forces, circular motion, they're the same. And then energy and momentum, they're kind of the same. This takes me through January. And then you take the motion equations combined with F equals ma, you get the work energy theorem, the impulse momentum theorem. So this is what I do. Although forces, I love forces, and that's at the heart of mechanics. Momentum sort of puts it all together. And this is the best of momentum. So this is kind of 2.5 weeks in about 15 minutes. We're a big hockey school, so I'm not sure if you're aware, but there's actually 4 kinds of hockey pucks. You got your regular hockey puck, then you got your lighter hockey puck for the little kids because they're not that strong. Then you got your heavier hockey puck for the to improve hand-wrist coordination, and then you got your white hockey pucks, which are used for
Practicing tracking, visual tracking?
Yeah, visual tracking, because against the white hockey rink, the goalie can't see it.
Oh, right.
I've learned a lot through my physics teaching for kids. So you can also get a free Xeno puck. This can be used on any surface. It was developed in South Florida, where I used to live. So just write the company and get them for free. Xeno pucks. The orange puck brings up a good point about bat weights. If you buy a bat weight, it makes the bat heavier, so that in practice you develop your muscle strength, and then when the game comes, you become a better hitter. But the research shows it's an actual opposite psychological effect. It really doesn't work. I just found that out a few weeks ago, researching this online. So it really doesn't work. So, and I'm a big softball person. I play softball every summer. So that's the bat weight here. If you need softball bats, just ask your kids, and they'll give them to you.
What is a Xenopuck? What does that mean?
I don't know. It's just the company name, a Xenopuck. It's a uniform plastic, the same weight as a regular black puck.
Got it. Okay.
Is that X or Z for Xeno?
X.
X.
X, yeah, X. What else? Then related to baseball is, I don't know if you're aware of the Vector O-Bat. This came up back in the day for $280. I got it for free. They're on eBay used, so the 3 holes were meant, if you swing this way, you could swing the bat faster and exert and more impulse to the ball to make it go further. So I've never used it, but I just like getting free things.
Yeah, that doesn't look like a big reduction in
I was going to say, like, has that been shown to work? I feel like that's not a terrible decrease in wind resistance.
I don't know. I give you the website to find the research on that right here. So I'm not sure if it really works. I'm not buying this one.
As a pump fire, I don't think that's legal.
Yeah, I was going to say that.
Years ago, they used to have a water-filled bat with a water you have to handle them.
I still have one of those.
Loaded bats are also not legal.
Right. So that's the Vector O bats. Okay, rocket engines. Everyone in your bag has a free rocket engine. Alyssa will appreciate this. I mean, we all teach about impulse and momentum, but honestly, I've never seen the word impulse in real life. The only place I know of is a rocket engine. So if you teach astronomy or doing rockets on the last day of school it really is spectacular. And each rocket has a little rating on it. And so here's from Estes, and it gives you all the Newton seconds and all that. Again, that's the only time I've ever seen Newton seconds in real life. So here's a free rocket engine, and these go in the Estes kits like so. And of course, the bigger the letter, every letter doubles the impulse. So I would stick to A and B engines. The C's and up go super high, and then the wind's going to take it and up in the tree. So stick with the lower engines. But it really is a fascinating display of physics.
In my case, it landed in the lake.
In the lake, there you go. Right. So there's that.
Of course, there's impulse control. I talk about that all the time.
Okay, then everyone gets a pair of Happy Sad balls. I think you know it. If you look in your bag, there's a pair of Happy Sad balls, $8 a pair. Flynn sent me 36 pairs for free. I didn't think they'd be able to do that, but they did. Of course, they also said, here, make sure to give everyone your 10% off. So these are from Flynn. Happy Sad balls. A happy ball is just happy, and a sad ball just kind of like that. This one compresses really quickly and then takes a long time to come back. You can heat them in a hot water bath or cool them in a cold water bath, and they do weird things. I put the results on there.
How do you know which is which?
They squeeze differently, they roll differently, and they're free. I love free stuff.
Liquid nitrogen.
Liquid nitrogen, yeah. So we made this at the AAPT. If you glue them on a little sliding PVC here, and then you can discuss what transfers more impulse. Do you want a ball that rebounds, or do you want a ball that sticks? And almost every kid, even the brightest kids I've ever taught, they all think it sticks because it carries the momentum. But as we know, impulses change momentum, and momentum is a vector. And so 5 minus 4, it's really not 5 minus 4, it's 5 minus a negative 4. So I'll do the sad ball first. You have to go from the same height more or less. So no more or less, something like this. There's the sad. There's the sad. But if you flip it around, then the happy hits. And again, it's action reaction. It's got to stop it and throw it back out. Physics rules. Physics rules.
That's so cool.
So that's happy sad balls. Also, the company Waboba sells balls that bounce on water. I wrote them. They sent me 60 of them for free. So you each get either a large or a small Waboba ball. These were sold in FYE stores, FYE CD stores back in the day. And then I wrote the company, and they sent me a few. So everyone gets either one of these or one of these. These supposedly bounce on water. There's also a couple of handouts on the physics and chemistry of the happy and unhappy balls. And then this is my impulsive behavior lab. You take a ball and bounce it on 5 different surfaces and measure the rebound height. So that's what's in your bag. You have 5 or 6 different balls. I had over 200 balls. I don't want them anymore. So you reap the benefit after 30 years. So I just drop it from a height of 1 meter, and then we measure the rebound. They do that 3 or 4 different times, different heights, things like that. So this is an actual copy of my lab. I'm low tech, no computers at all, never. I'm all low tech. So that's everything on the front page of this handout, yeah. Okay, on the back page are applications of this. Newton's cradle here, I always start with 2 balls. 5's just too complicated, and you can do the simple action reaction. A pushes on B, that makes B go forward, but B pushes back on A, which stops ball A. So I like to start with that one, and you know, and do things like this. I'm sure you've all done these before. Right? So I won't spend a lot of time on this one, but I put a question at the top of the page. I'm sure you, and on top of the back page, you know, if you bring two come in, 2 will go out, but momentum would also be conserved if 1 ball popped out at double the speed. In fact, there's many ways for momentum to be conserved, but only one way ever happens. And does anyone know why we only get 2 balls? Yeah, I think. And what is the reason? Yeah, if 1 ball popped out at twice the speed, you wouldn't conserve energy. The energy would go up by a factor of 2. So that's I used to give that as a bonus question to my.
I think it's fun to do both balls.
Right. Yeah, you can do it.
The ones in the center not doing much of anything.
Or if you do like 2 on one side and 1 on the other.
Yes.
Really good. That's cool.
I'm not going to go through all those. I'm sure you've seen
My kids always
them.
want to like test every possible combination.
This is the magnetic version, the Magna Swing. It's not made anymore. You get them on eBay for $14. There's plenty of them available. It's not as good as I wanted it to be, but you know, it's kind of chaos.
So maybe some kind of a damper would help.
Yeah, it comes with a reg magnet. There's a red chaos magnet, which this one didn't come with, but you can get them on eBay now. Nobody really wants them.
I think the kids would want you to have one that looks like that, so that they can just start it and just watch it. Yeah. Not watch you. They just want to watch that.
Right.
What is that called again?
The Magna Swing. It's on eBay. Nobody wants them.
Call it chaos magnet.
Well, it's an auction. You could bid 0, maybe you win.
Usually the minimum bid set at $1. Most places.
I don't think $1.
So this is the magnetic accelerator, and this is a magnetic ball in my left hand. So this works like the Newton's cradle, but there's just a little more friction, things like that. But that's not the intention of this. That's not the intention of this demonstration. There's a magnet ball here, and so I do a lot of peer instruction. I've been doing this for 20 years where kids talk with their neighbors and try to predict the result. So I got the magnet ball here, and I'm going to let it go, and I want you to predict what's going to happen. And then number 2, we're going to switch it. We're going to put the magnet ball there and then let it go. So why don't you talk in your groups of 2 to try to figure out what's going to happen in these cases? We'll just give you another minute. We'll just give you a minute.
Well, it's called a magnetic accelerator.
Because it's this going to
This is a magnetic ball.
I think it's a magnetic.
Those are not magnetic. These are not.
Remember when you have a moving magnet, which will cause metals to behave as if they're magnetic, but as if they're, so it's like inducing magnetism, right? So you're inducing magnetism in the system. I think there's also one here, and I think this one.
And when did they start?
Because you don't have, because this is stationary to begin with. So I think this is nothing interesting can happen. I think something's going to happen there. That's my prediction. Because magnets. That's my answer. Because magnets. That's like that answer. Because magnets.
This is how I do typical peer instruction in my class. I've got it for every topic all year. And then I would ask someone to share the result, what they think, and then etc. Does someone want to share what they think? Anyone feel really confident? Anyone bet money on their answer? I always say this. Anyone want to share what, is there a difference in results, same result?
I think I'm right.
Oh, rough crowd. Wow.
Please, well, a question that we were unsure about. Do you tell students if it's going to attract or repel?
No, it's just a matter, you know. Yeah, they know what attracts. You want to share your answer?
We figure you're dropping the magnet, right?
Yeah, I'm just rolling it. Yeah.
So we figure it's going to attract the first one towards it.
Okay, yeah.
Before it gets there.
Yeah.
So it might slow it down a bit.
Okay.
And then you won't see the same symmetry by where the ball exits.
Let's find out.
And I'm thinking the magnet might not be strong enough to bounce off.
Let's find out. Let's see what happens here. Well, that's kind of interesting.
That's pretty strong magnet.
Now we'll repeat. Now there's the magnet right there. There's the magnet right there. Any predictions now?
Yeah, that's going to pop off one on the far right.
Whoa. Physics rules.
There you go.
Semi-discrepant event. And you can do whatever variations you want on this. So. Okay, the last demos are actually wear a bulletproof vest. I only wore it in the classroom for obvious reasons. I wrote various police academies. There's Kevlar in here, which degrades every 5 years. I went around Princeton and got free bulletproof vests. This was before 9/11. I asked one officer, can you please shoot it against a tree? And so here we go. Here's a 40 caliber, a 9mm, and a 38 caliber, and it really squishes. I'll pass this around. It smells like the officer who wore it for 5 years. You can't get that smell out. So I'm wearing a bulletproof vest. After this, I do karate. That'll be for another demo day. I just don't have I need a truck.
Well, while you're on that, I've heard that you can increase your karate swing by pulling back your hand.
That's not true. We'll get to that.
Okay, it's a balance.
These are rubber bullets I got on eBay. This is version 1. This actually killed some people. This is version 2, a little softer. You can legally buy these. These are rubber bullets. They're used for crowd control, riot control, to disperse crowds. Those are real rubber bullets.
Yeah. Is that the size? Is that the caliber of their shot?
Yeah, that's like it's a huge gun. You know, it fires I think 6 out at a time.
Wow. It's just like. I always thought they were smaller.
And then this is bulletproof glass. You can get this on eBay. Just be nice and they'll send it to you for free. This is real bulletproof glass they use in the Pope Mobile at banks. And so the guy in Colorado said, can you shoot one with a bullet? He goes, yeah, sure. So he shot one with a bullet, and the actual center is actually raised up, and there's an outer part that's going in a bit. He was so close that the shards came back and sort of tore his arm up. He was bleeding. I'm like, I'm really sorry you did that, but thank you for doing the demo. So, and this is the 357 Magnum bullet. This isn't the one he used, but it looked just like this. So I'm against all ballistics and firearms, but I use them in class to teach physics, and momentum is the ultimate topic where all the mechanics ideas come together.
Wait, is that the bullet that actually?
No, this isn't the bullet.
But it has to get searched.
But it's a copy of it.
It's a copy of it.
Yeah.
Again, I would follow this up with karate and all that, which I was going to bring, and I'm like, I don't have no room for this. So next time we'll do a whole karate demonstration and things like that. You all get to try it. It will leave an impact. How about questions? Anybody?
I always love your demos.
Thank you. I love physics. It's my passion. I do it. I don't need the money. I love what I do.
Don't say that too loud.
It's interesting because I didn't realize that there were different types of hockey pucks.
Yeah, I didn't either. I
feel like it would be fun to, you know, if you had some type of surface, like let the kids kind of test hitting each one.
Yeah, you could with the hockey stick, yeah. No, I told him to get the puck out of here.
Oh, that's weak.
And there's the street hockey ball.
I never knew about this until a student brought it to my attention.
The white ones.
With what? Yeah.
And then there's the floor hockey ball. Like a different.
The thing is, I've always seen those. I've seen the white ones, and I never knew what they were
Because the
for.
goalie can't
Yeah, but it makes sense.
Yeah, because so the goalie
Because
just
you
goes
go,
on this.
you know, you go to like skate shop.
Stick it, and it sort of
and
figures out where it's likely to go.
skating, and there's also the summer and all that stuff.
Well, that's good.
So I was always like,
3 hours. You can see where it's going from this stick.
Any other questions, anyone?
thank you so much.